Today we are explaining proxy exploration and reusable guidance, a paper that proposes proxy-guided update signal transfer for more modular language model post-training.
What is the practical problem with post-training that this paper wants to solve?
The paper separates post-training into two jobs. Reward optimization explores which behaviors earn high scores, while policy alignment teaches a model to follow a useful distribution. Existing pipelines tie those jobs to the same model, so the expensive search must be repeated whenever the target model changes.
Why is that coupling more than just a cost issue?
Because the explored behavior stays attached to the model that discovered it. Parallel distillation can align several experts, but their exploration still depends on the policy being trained. That makes asynchronous generation, caching, reuse, and transfer across model sizes difficult.
What is the paper's way of separating exploration from alignment?
Proxy-Guided Update Signal Transfer, or PUSD, uses a smaller proxy model as a test up. The proxy searches with reward optimization. The system extracts only the change caused by that search, and the extracted change is transferred to a primary model that may be larger or different. The first design difference is therefore important. PUSD transfers a relative improvement, not the proxy's entire final probability distribution. That is the paper's route to weak to strong improvement and cross-model reuse.
How does the system represent the change made by reward optimization?
For a prompt, a partial response, and a candidate token, the proxy compares its optimized policy with its original policy. The difference is the proxy update signal shown here.
What does the sign of that difference tell us?
A positive value means reward optimization made the proxy more likely to choose that token in that state. A negative value means the token was suppressed. The signal therefore records a direction of change, and the proxy pair can be stored so the signal is available later.
Why not simply make the primary model imitate the optimized proxy?
Absolute imitation would bind the target to the proxy's full behavior, including its capability limits. PUSD keeps only the reward-induced difference, then applies that difference inside the primary model's own policy space. The stronger model is guided by the proxy's improvement without becoming a copy of the proxy.
If the signal is reused many times, what prevents the primary model from overreacting?
PUSD measures how far the primary model has already moved from its own reference policy. That anchor log ratio is subtracted from the proxy signal, so the transfer becomes more conservative when the primary model has already absorbed the suggested change.
Where does the calibration coefficient enter the update?
The transferred utility is the proxy improvement minus lambda times the primary anchor shift. A larger lambda penalizes movement away from the primary reference more strongly. A smaller lambda lets the primary model follow the proxy signal more aggressively.
How is that utility turned into an actual training objective?
The primary policy weights the calibrated utility by its current token probabilities, and training maximizes the expected value over token states. The proxy before training, the optimized proxy, and the reference policy stay frozen gradients update only the primary model. The experiments use Q13 models at 1.7b, 4b, and 8b parameters in math and code. Proxy experts are trained with GARPO using verifiable rewards. Then their signals are transferred to primary models and compared with the base models and direct reward optimization.
Do weaker proxies actually improve a stronger primary model?
Yes, en masse. Transferring the Q13 1.7b signal raises that average to 37.2, while the Q13 for B signal raises it to 47.5. The gains are measured against the same 8b base. The benchmark pattern is also concrete. With the 4b signal, AIME24 reaches 62.5 versus 24.4 for the 8b base. The transferred change can therefore produce larger gains on the stronger model than the proxy model achieved on itself.
Does the same transfer idea work outside the math benchmarks?
It also improves code performance. For the 4b to 8b transfer, the average mean at 16 score rises from 55.9 for the 8b base to 60.5. Human evil changes from 80.5 to 83.1, MBPP from 70.6 to 73.5, and LCB from 16.7 to 25 points IRO.
If a signal is reusable, how much training can it save?
AQ13 for B proxy explores for 500 GARPO steps, but the exact same signal improves 1.7b, 4b, and 8b primary models in 50 transfer steps each. Their average math gains are 16.7, 30.5, and 30.2 points over their respective bases. The expensive search is separated from the cheaper alignment step.
Can a signal survive more than one transfer between models?
It can, although the signal drifts. Direct for B to 8b transfer reaches an average of 30.1 points of gain, while for B to 1.7b to 8b transfer still gains 26.6 points. So transitive reuse works, but each intermediate transfer can alter the direction.
How close are proxy-discovered signals to signals explored directly by the 8B model?
Direct exploration by the 8B model remains slightly stronger overall. The 4B proxy comes close under a comparable budget, while the 1.7B proxy improves when its exploration grows from 500 to 800 steps. This shows both a strength and a boundary of PUSD. Better proxy search and better data can raise signal quality. But a small proxy is not automatically equivalent to direct exploration.
What are the main limitations that remain after these results?
The quality of a transferable signal is bounded by the training data, the proxy's exploration strategy, and how the signal is aggregated. The paper also uses a constant calibration coefficient, even though the best transfer intensity can vary across states. Future work therefore needs stronger parallel or multimodal exploration and calibration that adapts to the local relationship between proxy and primary distributions. The central lesson is that post-training does not have to make the final model perform all the exploration itself. PUS decompresses reward-driven improvement into a relative signal that can be generated as instruction, cached, reused, and transferred to stronger models, while calibration controls how strongly each target absorbs it. That is the paper's contribution, and that is our wrap-up.